Okay, we're still maybe waiting on a few other people, but, and I heard there's an accident out there, so that might be holding up a few. So typically, the big welcome here, it's terrific you're here. This is going to be education, and a lot of you might know some of this, but we're here to fill you in. People have been working this for a long time, different people from different areas, and we've all come together here. It's the first time that all these disciplines have come together in one room to then reach out to the public and our local elected officials to let them know what's going on. That's the big thing here. And so nobody else is coming in. So before we officially begin, if we do the Pledge of Allegiance, because this is a very American thing that you'll see what we're talking about here. So this is for all of us. So there's our flag. So I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Awesome. So just a few quick words about NDIA, National Defense Industrial Association. And we have two board members here, Dave and Reggie, sitting right there. And Bob's with us, a few others of you in the room. Might be some more coming. This organization is the interface between industry and the military. So we came up with our own slogan here, and Las Vegas is the city of innovation. This is the Innovation Center with NEV for Nevada in it, but their whole thing here is to bring out innovation. And then AFWorks showed up here very surprisingly, probably about a year and a half ago, and that's the Air Force's hub for innovation in the United States. They chose Las Vegas. How fortunate is that? So with this theme of innovation, you see here, this is just a very powerful statue that I saw. And it shows a scene in Vietnam where someone's been badly wounded, and this, well, I can't really point to both, but the little inset in the bottom right is the guy in the back carrying the guy who's been wounded. And it really gets you and lets you see what people go through to defend this country. And that harm's way is what we have an opportunity here to work for the future. With small nuclear reactors and deployed throughout the world to remote locations, you don't have, for instance, the fuel supply trucks that are great targets where a lot of people have been hurt and killed. So that's a big thing, and not to mention the efficiency of setting up a remote location. So this is our way with this project of bringing innovation to avoid people unnecessarily being in harm's way. We did that. This picture, you'll know what all this stuff is very soon if you don't already. This is the topic of what we're doing today. And this will be up for a reference point, but you'll see what all these are. Top left is a small self-contained nuclear reactor. These things are becoming a reality. France has been in leadership with this. Then there's another depiction of, you see like a little guy there standing next to it. So these things come in all different sizes. It's a new industry in the United States. The standards aren't there, but they need a customer. And that's what we're here to build, that interface of military customer. And then you can even see one on a truck up there. And the big picture is these, think of them as big batteries that power what's called microgrids. And a microgrid is just the opposite of the macro grid that powers this country. A little inset of that to the right. It's interconnected. You've heard that phrase, what happens if the grid goes down? And that's down on the bottom. And the purpose of this today is to begin that journey that will eliminate that question from our vocabulary. Because instead of one big grid, tens of thousands of them is the big picture of this. And the door opener to begin this is the military. And even better than that, Creech Air Force Base right in our backyard has been designated by the head of the Air Force as like this is where we would like to get this started. So we're very fortunate in Nevada. Now I know there's a big energy in Nevada. Again, energy is the wrong word. Nuclear isn't a good word here. Yucca Mountain and the plutonium shipments have been a big thing. But all I ask is that everybody look at this. This has nothing to do with that. This is zero to do with that. This is its own thing. And my analogy is like if you get divorced, it's like, well, you don't say that all men or all women are bad after that. There's good things. So this is a good thing. So the other stuff, it's going to go. Whatever it's going to do, that's not what we're concerned about here today. Our big focus is on the education with this first. This is very important. When Bob showed me this vision, I said, wow. Little analogy I just used, the old cell phone. Make believe it's 1950 or 60. You have your dial phone and someone shows you one of these and say, this is what they're going to be using in the 2000s. You go, wow, really? This is the same kind of paradigm shift. So just ask that your open mind, keep your mind open to understand that and the education that we're going to bring you from this. Big picture is no more question what happens if the grid goes down. It's a little history of America. This is kind of important. These are fundamental concepts. Our industrial age has brought us a huge dependence upon electricity. But unfortunately, the ability to supply robust electricity is on very shaky ground. And that's because it's a growing big grid that's very vulnerable to EMP attack, a solar flare, any number of things. There's even been situations where they've lost power and they didn't even really know why. So we're very vulnerable. But turning the big grid into tens of thousands of small grids, each being served by its own big battery or nuclear reactor, is the solution to this. And it's probably a 30 to 50-year solution, but these are the first steps today. So you can see the little power thing on the right. So I just wanted to show it's like we're very vulnerable. Let's picture if you didn't have power for a week. Your food goes bad, the cell phones aren't going to work because they can't get fuel to the diesel generators in the cell towers, so forth and so on. No more U.S. as we know it. This is our intent here today to begin that alternate road. There's the big grid, and this kind of summarizes it. Huge grid, interconnected, a mess. Powered by a few, in quotes, a few huge power sources, big generating systems. Instead, lots of small ones everywhere, each having its own power source. And then we'll just leave this up because, so this is the thing I mentioned in the beginning. You're going to understand all this as we come through and talk, because the main talk today is all about these small reactors and then about the microgrids. And there's a 3-minute excellent video that will reinforce everything here. That good. It's an excellent video.
SMRs are the next evolution of nuclear energy, a type of nuclear reactor designed to be smaller in size than a traditional reactor. They're based on the same science as larger reactors, using fission to create heat, which can then be used to generate electricity. Small reactors have existed for more than 50 years, since the beginning of reactor technology, like the experimental reactor at McMaster University in Hamilton. Interest in SMR technology is growing across the industry and around the world. There are more than 150 proposed designs worldwide. Canada's energy needs are well suited for SMRs, as they offer the potential to provide clean, reliable electricity at manageable cost for both on- and off-grid communities. SMRs have 3 potential areas of application in Canada. For communities already connected to the electricity grid, SMRs provide a clean and reliable source of electricity to augment the current energy mix, enabling the development of renewable technologies to support environmental and climate change goals. This is particularly useful in provinces focused on lowering their fossil fuel generation. For communities not connected to the grid, particularly in northern remote areas, SMRs offer a solution to improve access to reliable electricity generation and reduce dependency on diesel energy. They can support improved health and environmental well-being, social development, and economic benefits. And SMRs can be a significant asset to heavy industry, like oil sands producers and remote mines across the country, who could benefit from the reliable and clean source of heat and power from SMRs. Although the basic science is the same, SMRs are an evolved technology and have advantages that make them beneficial in situations where a larger, grid-connected reactor may not be an option. They're smaller in size, both physically and in their land footprint. They are modular in that they are factory constructed and then delivered to site. In many cases, they are delivered already fueled and can operate for many years on the initial load of fuel. And they have other uses beyond electricity generation. They produce heat that can be easily used for other applications like district heating for commercial or residential needs, hybrid energy systems, water desalination, or heavy industry applications. SMRs can augment the baseload generation from traditional reactors and provide a reliable and diverse energy mix. At OPG, we have the versatility and experience to fill various roles in SMR development as owner-operator, operator, or project partner, thanks to the strengths we offer. And adding SMRs to our generating portfolio aligns well with OPG's goals and values. We are already a leader in clean energy and innovation. SMRs will augment our generating fleet, which is already more than 99% free of smog and carbon emissions. And finally, SMRs will provide growth opportunities for our company and support environmental, social, and economic prosperity.
Okay, so that wasn't intended to be advertisement for that company. It's just basically, it was an excellent video, and it gives you a feel for the seriousness. There's a number, and we'll get into this, number of companies in the U.S. that would love to do this have this as a product. So, but they need a customer, and we're working on that. So let's see. Next, Bob Frank is going to come up, and Bob opened the door for me into all this stuff. And he and Jim Marchant had the vision in the beginning to get this all going. And then when they found out about NDIA here, we've joined up and haven't looked back. So Bob's had a few health issues, but even so, he is here today. It's terrific.
Sure. Thanks, Marty. I really appreciate seeing all of you here today, because I have a good appreciation for the amazing breadth and scope of expertise that you bring to this event. And I assume Marty is going to list the members in the future, not the members, but the attendees, so that you have an idea of who showed an interest in this particular program at this time. Basically, what I wanted to do was kick off the event with former Assemblyman Jim Marchant, who's going to be the panel leader for your discussions this afternoon. But before I do that, I want to talk to that chart. I'd be surprised if very many of you have ever seen a chart like that before, because from a global point of view, I had to stitch it together from a variety of satellite pictures that were displaying the lights on around the world. And of course, it's not dark around the world all the time. And but it brings home what Marty said about what's at stake for our country and for the world. It's more about clean air. It's more about clean energy. It's about survival of the human race for those that don't have electric power. Look at Africa just for a second. if you've ever been to Africa, you know how big it is. And you know how impossible it would be to duplicate the power grid that the U.S. has. Impossible. So what's going to happen in order to get Africa, more South America, more of the underpopulated areas capable of having modern civilized power? Small nukes are the only way to do it. I guess I would say to you that the small reactors have been really interesting to me for about 3-4 decades because in 1969, yeah, I said 69, I was in Vietnam for 3 years, and my job was to, as a logistician, to maintain logistic support to the Air Force photography mission all over Vietnam and Thailand. 17 different bases, all of them having to run off of power generators, diesel generators, all of them frequently failing, all of them having to be operated and supervised by my team, which was almost more than we could handle, because it's really hard to keep old diesel generators running 24/7 when they're really only designed to run for maybe a week or two and then get reestablished, right? Resuscitated. But to think about running them full time, year after year after year, you can imagine what my poor engineering team had to deal with to keep those power systems going at full speed and at standard operating. Now, if they had failed, any one of them, then part of what President Johnson wanted in terms of movies of the war every week would have failed, and we all would have gotten fired or replaced very quickly, which is what happened to my predecessor. So the urgency of trying to find a better way of supporting combat operations overseas, other than diesel generators, has been a burden I've carried for almost 40 years. Even when I was in the Pentagon, I did everything I could as in charge of Air Force supply policy to find a way to make something happen. But I couldn't find out anything at that time about small nuclear reactors because that was in 1982, 83. So when I met Dr. Craig Smith, who you'll meet here as a fellow Nevadan, but also a nuclear engineer and over at Monterey for the Navy, all of a sudden I started getting more knowledge about what's possible for a solution. And if you watch the headlines in the newspaper almost all the time, you'll see disinformation being passed out in the media about the fact that it's dangerous, it can kill people, it can do all kinds of bad things, and this is strictly false. Strictly false. But there are economic business interests by other power systems who know full well that if we're successful in launching a project like this, and this is the only one of its kind in the country that we know of, everybody else is studying it, writing papers, publishing in Forbes magazine, doing videos on TED, and so forth, trying to educate the people. But our program is quite different. I want to challenge you to listen for the differences in terms of solutions that you're going to hear this afternoon, because you're going to hear solutions in this place that you won't hear any place in the country. It's not being sponsored, and we're hoping to get Nevada on the map as a engineering application center of expertise to bridge public partner, private partnerships so that we can start manufacturing these things and deploying them for national security and for other critical needs to protect us from losing the grid and so forth. So from that point of view, although this chart is focused on the global problem for electricity, I'd like for you to look at it in two different ways. One, what happens if the lights go out? And we know for a fact, ever since the 60s, that enemies of the United States or the free world could take our grid down, probably by, it was classified at that time when I was in the Pentagon, but it was, you could take out 12 transformer stations on the East Coast, 12 out of hundreds, and take our grid down with an EMP weapon that would take it down for maybe 6 months to a year. And as Marty mentioned before, we know for a fact that most of those transformers cannot be replaced in less than a year. And they're only manufactured in Korea and in Europe, not in the U.S. Pardon? They brought it back in 2014, but it's small scale. Small scale, thanks. So we don't have a ability to buy backup spares like a good supply officer would, because first of all, they're too expensive, and secondly, they're all different and all kinds of problems. Okay, so without too much more to be said, what I'd like to say is that please focus on taking away from the presentations from this expert panel here, who have been very carefully selected for their vast experience, hands-on experience, unlike what you read about in the paper, are people that actually don't know what they're talking about. They have no degrees. They have no experience in running power plants. They have very little experience in knowing anything more than they read. It's what they read is what they say. So you're going to hear stuff today that you don't read about, but you're going to learn about, and we hope to start promoting it on a broader basis. So with that introduction, I'm going to introduce Jim Marchant, who is my original partner with Nevadans Can, and now with NDIA. Nevadans Can was formed as a nonpartisan, originally as a nonpartisan organization to support issues in our time and to try to stay away from political haranguing and focusing on what needs to be done for our society. And energy was the first one we took on. Jim volunteered to help. He was in the, actually it was before he got into the assembly in Nevada, but he carried the ball well while he was in the assembly on behalf of our program and on behalf of nuclear energy and about making Nevada great again from a nuclear power point of view. And so we've asked him to be the panel leader. He doesn't claim to be a nuclear engineer or a scientist, but he is a very successful small businessman from Florida who can afford to retire at his young age and do whatever he damn well pleases. So without further introduction, Jim, please come up.
Thanks, Bob. Like you've heard, what we're trying to do here is to provide an education for everybody, if you didn't already know, about why what we're doing here is truly a necessity for our country and for our state. We have a national defense, national security issue, and we have a solution for it. A lot of people are talking about it, but we actually have a solution for it. So what we've done today is we've got a panel of remarkable experts. I'm just honored to be in the same room with these guys, and it's truly an honor to work with these guys. So what I'm going to do first is allow each one of them to kind of address all of you and give them a little background of themselves, and then we'll jump into the questions that are going to answer a lot of your questions and hopefully go forward.
Thanks, Jim. My name is Chip Martin. I have a PhD in nuclear engineering. I previously was working on in the U.S. Capitol in the House of Representatives as the Glenn T. Seaborg Science and Engineering Policy Fellow. I worked in the office of Congresswoman Marcy Kaptur. She's from the 9th District of Ohio. She currently is the chair, the gavel holder for Energy and Water Development in the House Appropriations Committee. Before that, I was the chief nuclear officer for a science and engineering firm responsible for the operation of 4 nuclear reactors and 3 other nuclear facilities. So my responsibility was to keep those facilities safe and fully operational, as well as meet all of the federal regulatory requirements. Before that, I worked for the Defense Nuclear Facility Safety Board. That's an oversight organization similar to the Nuclear Regulatory Commission, but we oversaw federal nuclear facilities as opposed to civilian nuclear facilities. Before that, I worked for the Secretary of the Air Force doing nuclear weapon development studies and also other nuclear science and technology studies. I worked with Dr. Teller for a little while. Before that, I worked at the Department of Energy in their nuclear energy office. I was responsible for I wasn't the only one, but I was one of the program managers for the SP100 program, which was a space power reactor intended to fund or to provide power for the Strategic Defense Initiative, neutral particle beam, and other space weapons that were being developed at that time. I got my bachelor's degree from North Carolina State University and my master's and PhD from the Air Force Institute of Technology. Oh, one last thing, my comments today are my own, and no one should infer that I'm speaking for the U.S. government or any agency of the U.S. government. They're my views only.
Famous disclaimer.
So my name is Craig Smith, and before going through my background, I would just like to once again recognize Colonel Bob Frank, who was in the audience and who spoke a few minutes ago, and thank him for his leadership in this initiative, and also to thank the NDIA for sponsoring this event. So my name is Craig Smith. I received my PhD in nuclear science and engineering from UCLA many, many years ago. I won't say how many. After receiving my graduate degree, I served a period in the Army as a commissioned officer. And following that active duty period, received a reserve commission and continued on for another 16 years as a nuclear plans officer in the U.S. military. I also had in my career work in the consulting industry, nuclear consulting industry, with 2 companies, Science Applications International Corporation, where I was a vice president, and Booz Allen and Hamilton, where I was a principal. But my main career employment was at Lawrence Livermore National Laboratory, where I ultimately became Deputy Associate Director for their energy programs, and led the development of one of the technologies that has been graphically depicted here, a small nuclear reactor that was transportable and was designed around the idea of prevention of proliferation. At around 2004, an arrangement was made between Lawrence Livermore Laboratory and the Naval Postgraduate School in Monterey, part of which created a chair professorship there, and I was asked to assume that position, which I did until I retired from Lawrence Livermore Lab and then accepted a direct appointment as professor in the Department of Physics at the Naval Postgraduate School. And that's my current employment. I'm also a resident of Nevada. I live in the Reno area and have been really a long-term resident. While at Lawrence Livermore Lab and subsequently have continued to work in the field of advanced nuclear reactor technology, first with a system, as I said before, was a transportable, autonomous controlled system that was intended to be a system that you could place virtually anywhere in the world to provide reliable long-term power as sort of a nuclear battery without undue concern about the proliferation risk. I was asked by the Department of Energy to help organize a committee internationally on related technologies to this as part of the Generation 4 International Forum. And when I switched from being a Department of Energy laboratory employee to an employee of the U.S. Navy, the Department of Energy opted to continue that relationship, and I continue to serve in that role. So my experience is centered on advanced reactor systems, and without going on any further, I'll just say I'm happy to be here today.
Hi, my name's Mike Barrier, and I just want to preface what I'm going to say by mentioning that with so many brilliant people here, chances are I won't get another chance to talk. So I'm just going to take like a couple minutes to talk about my affection for microgrids. This has been probably 30 years in the making. I got a degree in economics from Berkeley, where I studied energy matters. I also spent time in the military telling my story. And microgrids are a passion with me. They are a part of reality in this country already. You really, when you think about like an aircraft carrier or a submarine, what you have is a nuclear-powered microgrid. And of course, the conversation is just now evolving in that direction because if we look at the military's handling of things nuclear, I think without question, they have the most outstanding record of any stewards of nuclear power anywhere in the world. And so folding into the conversation the subject of microgrids really kind of speaks to who we are as a people, that we can coincide with nuclear power for everyone's benefit. We need look no further than 29 Palms or Yuma, Arizona, to see that microgrids are already in use, powered by wind, by solar, by other means, to which we can now add to the conversation small-scale nuclear reactors. The point here is that microgrids are not pie in the sky by and by. They exist today all over the world and really are beneficial. However, I just want to add, for many people in the United States and elsewhere, there is sort of a shift in consciousness away from large-scale centralized facilities toward decentralized facilities that needs to become part of our consciousness. Anyway, thank you very much for letting me be here, and again, that's Mike Barrier.
Hi, Ron Frost. I like this concept on the microgrid. The first microgrid I know about was on my grandfather's farm. It was a small DC wind generator up on the windmill that powered a single light in the milking room. That was the beginning of microgrids in the United States. And in some places of the world, that's still the only power source that's out there. Eventually, I got a chance to go to Kansas State University, get my bachelor's degree in nuclear energy, nuclear engineering. We had a trigger reactor there, small reactor. The whole thing would fit in about half of this room plus a little bit of basement space. Trigger reactor had one of those unique properties. You worry about, oh, what if the control rods, you pulled all but one of the control rods out of the reactor and then you used air pressure to blow the last one out. And the reactor would go whoop, whoop, and go up and come right back down. And it was really neat to do because I got to go up on the top of the reactor itself one day to start the spinning piece of paper that we were going to graph this on, because we didn't have electronic systems to do that. So you flip it on, you run back down, they press the button, blow the control rod out, you run back up, shut it off, and you've got this little tiny blip of power being produced by the reactor. Reactors, if we do the right thing with them, are completely safe. You know, fast forward, the Air Force sent me back for my master's degree in nuclear engineering in nuclear weapons effects. One of the most fun things I got to do is come out here to Nevada and direct a nuclear test out on the Nevada test site. I was a technical director on Misty Rain, spent about $60 million of your money in a few tenths of a fraction of a second, and we got some good data. What we were doing is trying to decide how much radiation U.S. military systems could handle and still function. So we actually had some effective warheads. I had a complete communication satellite that thought it was out in space that was hit by the radiation. That was a cool thing to do. So thank you for spending those dollars for me. Later on, got to go create an Air Force Wargaming Center, again looking at military structure, and then how do you connect something called the Air Force Wargaming structure and system to other systems across the country and do it securely. You know, how do you protect all those electronic systems? So dealing with some of that. Finally, I ended up my career with the Air Force at Headquarters Strategic Air Command. My little shop of about a dozen people had the responsibility for strategic survivability of nuclear systems for all of the SAC weapon systems, missiles, aircraft, bombers, communications. Left from there, do Kansas, primarily emergency response for radiation. Got to do some help with FEMA, help training state and national responders, and then a little work with the International Atomic Energy Agency to put together some training materials for international responders to radiation emergencies. Finished my work and then retired here in Las Vegas with the Environmental Protection Agency as the director of our National Response Center for Emergency Radiation Response. Just prior to that, all of you remember Fukushima? Oh, we're all going to die from the radiation. My laboratory in Montgomery, Alabama was monitoring the air in the entire United States. We'd put out over 100 air monitoring systems that were continuously looking at the air. We did not see the effect except for about 2 hours. In Hawaii, we saw a little bit of radioiodine. Now, when I took that same filter and brought it back to my laboratory in Montgomery and counted it for a day and a half, yes, I could detect tiny, 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 tiny amounts of radioactivity from the Fukushima release. With the automated system, we were about 1,000 or 10,000 below anything that would have been effective, and you should have been worried about. Once I got it back at my laboratory, we were down a factor of about 10 million below a health hazard. So I've been pretty much doing radiation emergency response for most of my career. So that's kind of my area of expertise on the panel today. Thank you.
What I tell you, pretty impressive, huh? First thing we're going to discuss today is exactly what is a small modular reactor. So we'll start with Chip Martin here, or either one. Yeah, so let's just describe what exactly is a small modular reactor and kind of like why it's different from the current reactors, how far advanced is it now, and why it's safe.
Well, so let's start back at the beginning. Early reactors were generally small, but very early on, when it became a commercial entity, engineers realized that there were a lot of fixed costs associated with operation and licensing of a nuclear reactor, and so there was an economic pressure towards larger and larger systems to spread that fixed cost element over a greater output. And ultimately, it became almost part of folklore or almost a religious belief by nuclear engineers that you can't have economic viability in smaller systems except for specialized uses, such as powering submarines or research reactors at universities. I would say about 15 years ago, there was sort of a paradigm shift, a realization that large-scale reactors were becoming more and more expensive from a capital cost standpoint. So the point that the value of a large reactor could be a very, very significant fraction of the asset holding of a typical utility. And so there was a lot of financial risk that was associated with that. And there was further some realization that if you went to small reactors, you could sort of take the Ford Model T approach of making up for this scale reduction by multiple units, by factory fabrication, and by having reactors that are located closer to where their power is needed, thereby reducing transmission, and a dozen other factors. And so small reactors, small modular reactors became a phrase in the lexicon, and started to receive funding from the federal government for development. While at Lawrence Livermore Lab, we developed the S-STAR reactor, which was a small transportable reactor I mentioned before, which was really just one of it was sort of a leading edge, but one of many reactor concepts that had developed from that point. So the other parameter, which I think is a far more recent concept, is the microreactor. And so really, these terms are not precisely defined at this point. But a large reactor is typically something around 1,000 megawatt electric output. Could be bigger than that or smaller. And I think the official definitions were really, if it's above about 600, it would be considered a large reactor. And if it was from up to about 600, it was considered a small reactor. But now we've introduced this new concept of a microreactor. I like to think of it as a microreactor is something that is typically from the range of 1 megawatt, could be a little bit smaller, up to 10 or a few tens of megawatts. And that a small reactor is typically in the 100 to a couple of hundred megawatts, though it could be a little bit smaller and a little bit larger, and that the large reactors reside in the range above that. And so there's a lot of work being done in the immediate past and continuing now on microreactors, and there's a number of reasons why that's important. But let me stop there and see if Chip has something to add on that.
So one thing about this latest generation of micro and small reactors that's important is the latest ones are being designed to be inherently safe or walk-away safe, some people say. And the idea that they don't need any off-site power in order to be able to deal with the problems of loss of power. And they can be operated by a very small crew, 1 to 5 people perhaps. Unlike current generation power reactors that may require 700 people on site at any given time. So that's a significant advantage to this kind of reactor.
One other thought, again, from the military side of the house, the submarines and the nuclear ships, the newest of the submarine reactors will operate unrefueled for 30 years. Unrefueled for 30 years, providing all the power needed for that ship to operate for 30 years on the sea. So again, we know we can do that. Now, are we going to do that level with the new small ones? Probably not, because the enrichment of the fuel and some of those things, we try not to have that outside the military, but we already know and we have demonstrated the ability to do those. When we take one of those reactors out, it's stored literally in a deep hole, but above ground and visible, because the Russians want to fly a satellite over and say, yes, they decommissioned that submarine or that ship's reactor. So those are all still available and visible. I've seen them.
And let me add one more thought on this. The compactness of a microreactor offers great potential for its ability to be protected from a security perspective. And this is, of course, especially important in the military, but it's also important for non-military government and civilian uses in providing assured power for critical industries and operations.
Not yet. We're going to wait till after. One of the things I wanted you to address is the current reactors require a lot of water. These new microgrid reactors do not. Is that the case? And if you could explain that.
So any thermal power generation has a certain inefficiency, and that inefficiency means that you have to remove the waste heat. This is true whether it's a coal plant or a natural gas plant or a nuclear reactor. Now, I would say for large plants, it is an issue because of the large amount of power that they generate. But I would point out that the largest nuclear plant in this country, I don't know if it's in the world, but in this country, is at Palo Verde, not very far from here in Arizona, and it's on the Gila River. Now, the Gila River flows with water only for a very short time each year. So it's not really a water supply that could be used for cooling that reactor. What they use in that case is they use wastewater, treated wastewater from local communities to provide all of the cooling that they need. So this is a problem that can be solved. when a reactor is cooled by water, that doesn't mean you have a continuous flow of fresh water into the reactor. It means that you have water that's being used in some way or another to cool and take away the waste heat. So it's isolated from the actual reactor. So now if you go down from 1,000 megawatts to 100 megawatts, that's 10 times less power being generated and 10 times less of a problem. Now if you go down to 1 to 10 megawatts, you've even further reduced it to the point that different reactor designs take different approaches, but there's one reactor concept that, for example, uses direct transmission of the excess heat into the surrounding geologic medium, so with no water at all involved. So the demands for water for microreactors are very, very small, at least in proportion with the size of the reactor and its output, but usually even to a greater extent than that.
And they would be self-contained also, right? Is that the way
reactor,
we're going?
if it's a water-cooled reactor, which is only one subset of the types of technologies that are being looked at, then the primary water that actually is cooling the reactor core itself is in a contained system. It's a sealed system, and so there's no major replenishment of water. It's just the same water circulating through and isolated from the environment.
Right. And describe the other materials that are used to do that
All
also.
right, so as an overlay to recent advances on the size of reactors, looking at small modular reactors and microreactors, there's another overlay, which is the Generation 4 program, which looks at advanced reactors as we go forward. It was initiated here in the United States, but it's really an international program now. And in that program, there are 6 different reactor concepts that are being looked at. And the main thing is the nature of the coolant that's used as a primary coolant. Some of them use water, but others use helium gas or gas-cooled reactors. Sodium is a liquid metal that's used. Lead is another metal which in its molten form is a very effective coolant, and molten salt is another coolant. So you have these advanced reactor concepts, and then some of them can be small, some of them can be micro. So it's sort of a mix and match environment that we're in.
Can you bury these reactors so they're EMP proof? Is that a...
Well, EMP protection is one of the critical needs that we're looking at now, especially in terms of military applications. But quite frankly, either EMP or as a natural event, a serious solar flare represent vulnerabilities to the overall grid as well. So EMP protection is a very important consideration. And in fact, I think there was a presidential directive signed
2 days ago.
Yeah, just
in his
today,
budget.
Directing, recognizing this vulnerability and directing the agencies to address these problems. Just a second. So the compact reactors, these micro reactors, are typically small enough that it is entirely feasible to bury them and use that as a protective measure, both for EMP protection as well as for protection against physical attack or natural events.
Right.
For those of you who have no clue what we're meaning when we say EMP, electromagnetic pulse.
Right.
If you want to go back to some unclassified numbers, if the right nuclear detonation occurs up very, very high in the atmosphere, you could put unclassified 50,000 volts per meter pulse over much of the United States. So if you had one of your old cars that had that roughly 3-foot little antenna sticking up, there'd be a 60,000 volt pulse come out of your antenna into your radio. Think what that would do to your TV, to your computer, to your power grid, which has miles of lines and wires. So yeah, we've been working this and studying it for a long time, pretty much on the military side, but that was part of my job at SAC, was to look at that issue.
Okay, Mike, you do get to say something here, but we're going to talk a little bit about microgrids and why these new small modular reactors would be an advantage to building these microgrids all over the country.
Wow. Well, I'm not a nuclear expert by any measure, but when you set out to design a microgrid, one of the considerations is what's going to be your peak power on, say, the hottest or the coldest day of the year, because everything has to be planned out well in advance. And so part of that process is what's called load stabilization. Now, with wind and with solar, you know, if the sun ain't shining, you may have an issue. If the wind's not blowing, you may have an issue. So we talk in terms of battery storage, particularly overnight. Elon Musk is a champion of battery storage, for example. But it is clear that a well-regulated small reactor, or large reactor for that matter, can be programmed to deliver a certain amount of power continuously 24/7. So the advantage to nuclear, whether it's integrated in with solar, wind, or other means, or if it's a standalone application like it would be with the Navy or a university-type reactor, is that there's no guesswork about load stabilization. You know that by studying an area's consumption of energy, how much you're going to have to produce to meet that need. Very simple.
We discussed how vulnerable our current electric grid is. With the implementation of these microgrids, how would you do that? How would you kind of migrate towards the microgrids from our large electric grid? And maybe describe, you know, why are we vulnerable right now, and then how would these microgrids solve that problem?
Wow. Actually, I'm from California. Anybody here familiar with California's plight over the last couple of years? What you have is a deteriorating asset base for the distribution of electricity, right? PG&E, where I did my internship many moons ago, went into bankruptcy because they're being blamed for poor maintenance of their power lines, which started this enormous fire. That wasn't any enemy activity. That wasn't no EMP. That was somebody forgetting to price into the cost of electricity the cost of proper maintenance of the network, right? And the year before that, I come from Santa Barbara. We had an enormous fire blamed on Edison this time, which started in Ventura, and you don't need to hear that story. But this is kind of a repeating scenario that there are issues with large-scale grids that can surprise even the best of us. Now you can factor in other people's worst intentions, let's say. And to the degree to which you think that that's an actual threat or not, I leave to your own imagination. But I do know that economically, financially, the disruption to communities, these large-scale grids, in a way, have let us down. Now, we could talk about 29 Palms. We could talk about what's going on in Australia. You saw a video clip about Canada. Actually converting from large-scale grid applications, it goes back to that paradigm shift of our consciousness. Can we visualize communities, military bases, or other government institutions being powered essentially off-grid, or powering in such a way that they can send and sell electricity out to the main grid without needing to receive electricity in? As it happens, I'm working on a proposal for the city of Lompoc, county of Santa Barbara, the state of California, and the federal government based on a similar concept at Vandenberg Air Force Base, which also has a world-class critical mission. It's really just a question of analyzing what are the energy needs at any given moment in time, which thanks to smart metering we are now capable of tracking, and essentially putting together your little Lego blocks so that you meet that need. In places like Lompoc, which I mention in particular because it's a utility enterprise community, they own their own electricity already. They already have and maintain their own infrastructure in the same way that the state of California does, in the same way that like the Lompoc Federal Penitentiary. Anyway, interesting study out of Victorville, if anybody's interested in a large-scale microgrid for a prison facility, but definitely Vandenberg. It's simply a matter of scaling based on need, and then you can cut that cord. It's really not that complicated.
The critical nature is, again, why we're talking about Creech, but going back to my nuclear test out at the test site, we assumed that the grid would go down while we were executing our test. We could not afford for that to happen. So we really built a microgrid inside of a mini grid so we could do that. My microgrid was motor generators inside the tunnel so that normal electrical power spun the motor, that spun a generator. They were both powering and then supplying batteries. So if anything happened, it kicked into the DC motor that kept running. Outside, we put a huge diesel generator to power them. Because again, we could not afford to detonate a nuclear device and waste $60 million because the power dropped. So again, the critical nature is why both the microgrid, small nuclear reactors, whatever we're going to do, have to be reliable. That's the critical piece.
And another consideration here is that a microgrid could be completely independent of the main grid, but more likely it will be connected to the main grid in a way that that connection can be severed, and so that it could operate independently. And so yes, in particular with the problem of assured power at critical military installations, it wouldn't really make any sense at all not to take electromagnetic pulse protection into account. Because why would you have an assured power microgrid that would be vulnerable to the same thing as the main grid? You have an electromagnetic pulse that causes a failure of the main grid. If it also causes failure in your microgrid, then what was the point in the first place?
Regarding safety, you mentioned a while ago that you could actually walk away from these new small modular reactors, and I know a lot of people are very interested in safety and not having a Fukushima around here or Chernobyl. Can you describe why it's walk away safe, that type of thing?
So many of the designs have very high heat capacity coolants. And so because of that, if you lose power, you don't have to provide external power to keep it cool. The heat capacity of the reactor and its coolant system is enough to allow it to increase in temperature but never reach a point where it might fail. So you're not going to worry about fuel melt in that case. In addition, while we say walk away safe, that doesn't mean we're necessarily going to leave them unoccupied, although
Right.
there are considerations for very remote sites where you might in fact do that.
Great, that answers the question. As Marty mentioned, we added a division to the NDIA for assured energy for researching what we're doing at Creech. And so why is Creech a great opportunity for us to start this process and develop these new reactors, and how can it benefit them?
Well, one thing about Creech is it has a very vital national security mission. So I can't say much about this, unfortunately, but just take my word for that it has have a very vital national security mission. And so they are very interested in obtaining some sort of assured power so that they're not relying on off-site power in times when they might lose it for whatever reason. Currently, they rely on diesel generators to provide temporary backup, but if you have an extended outage, you have a very serious problem at Creech.
Creech also happens to be immediately adjacent to a Department of Energy facility at the Nevada test site, where there's tremendous expertise, facilities, infrastructure to test and evaluate such technologies. So the interest in the military, it crosses all the services, and it goes way beyond a single critical Air Force base. And there's great value to be gained DoD-wide from a development of this technology at the particular location here, which is receives a tremendous advantage from its proximity to a DOE facility where you have all of these capabilities.
Exactly. How many of you are aware that the test site is actually assisting in the building of a small modular reactor to power Mars when we go there? All of you, okay, pretty good. That's how close it is. So we have a lot of technology near here, so we can use it. Are there other sites other than Creech? I guess the whole military can use this once we get it developed, right?
Yeah, so Creech, as I said, is just one example of many. There are peculiarities of each of these installations. Creech Air Force Base is a small installation that requires assured power, but not necessarily at a very high output level. And there are other major military installations which could also benefit from assured power, but for which the power requirements might be much greater. I recently had a couple of students in the business administration school take a look at naval facilities in the San Diego area. And by grouping 3 nearly adjacent facilities, they were able to gain all of the data on past usage to characterize what their critical needs would be, and then to look at reactors that in this case would fall into the category of small reactors rather than micro reactors. Furthermore, the Army, and I believe this is on behalf of the Department of Defense, is actively exploring the use of micro reactors for deployment for overseas missions. And they're looking at reactors that could be deployed, operated, shut down, and then moved to another location and continue operation. This is a very big challenge for land-based reactor systems, but it's not impossible. The Navy does it every day when they move their submarines around. So there are a number of different initiatives across all of the services that are looking at both fixed installation, domestic and foreign, as well as mobile applications of nuclear reactors.
It's also feasible that these could be used in the civilian community in case of natural disasters. Say Puerto Rico, they could be on a ship and be pulled into port and provide electricity for natural disasters. Is that correct?
That's correct. I did want to say something a little more about military utility of these small reactors. The military has a special problem when they forward deploy, and that is they have huge power requirements, energy requirements, and yet providing the fuel necessary to power them creates a logistics train that is vulnerable, and in fact in past wars has cost a lot of lives just keeping the fuel coming to keep the power on at these forward deployed locations. So the extent that we can resolve that problem, many military commanders are very, very interested in that.
One of my weird Facebook posts today was from a person who was visiting Pearl Harbor, and they were reading some of the history and such there. One of the reasons that we survived the Pearl Harbor attack and were able to continue the war in the Pacific is that the Japanese did not blow up the diesel fuel depot that was about 5 miles away on top of a hill. Had they taken out that fuel depot, we'd have had no ships functioning in the Pacific for a long time. So again, power capability, whether we have to ship it by land base, sea base, whatever, is critical. If you can't get the fuel there, none of the reactors or systems are going to work that need fuel. If you've got a system that carries its own fuel with it, like the nuclear submarine, nuclear cruise carriers or a small modular reactor, the fuel's already on board. You don't have to bring new fuel to it. Like I said, the newest submarines can run 30 years without fresh fuel.
One of the things we've been doing over the past couple of years is trying to establish at our test site or somewhere near here a research and development lab similar to Livermore or some of the other good ones to research and develop all of the above clean energy solutions to include our small modular reactors here. So what are the different, like we know we have wind and solar. What is the advantage of these reactors over wind and solar?
Well, that's sort of a complicated question, but
I'm glad you're answering it.
at the simplest level, I would say that wind power is great as long as the wind is blowing, and solar power is great as long as the sun is shining, and you don't have clouds. And the nuclear power supply will operate 24/7 without caring a bit about whether it's dark outside or light outside or whether the wind's blowing. So I think that's one kind of set of parameters. The intermittency of what we traditionally call these main renewable energy sources creates a problem on grid stability as well, and you really need a reliable, constant power source to overcome the peaks and valleys that exist in intermittent sources. So those are a couple of the factors, and I think Ron's going to have some more.
On intermittent, while Chip and I were at the Air Force Institute of Technology, a huge blizzard came through that part of Ohio. It closed all the coal-fired power plants. The coal was frozen in stacks. They could not use it. So it was nearby plants and nuclear plants in that area of the Northeast that provided the electricity for Ohio for the next week or so, because literally the coal was there, but it could not be used.
Yeah, and as a similar anecdote to that, I understand that some years ago, after having made huge investments in wind and solar in the United Kingdom, there was an unusual weather condition that came in with the dense fog and cold weather extended over a long period of time. And the wind and solar energy were not available. Fortunately, the French could power up their reactors a couple of percent and supply through transmission lines ample power to overcome that shortfall.
So because the question is maybe broader than just what we're talking about here, let me talk a little bit about the larger question, and that is many of us actually consider ourselves environmentalists. I consider myself an environmentalist. And I like wind and I like solar, and I believe that we should deploy those as rapidly as we can, as far as we can. The problem is when you look at climate change, the changes are coming at us faster than we can deploy the wind and solar technologies in order to moderate the amount of carbon that we're pouring into the air. And in many places in the world, China and India, they don't really have much in the way of alternatives. They're burning coal in order to propel their economies to become more modern. And that's just a fact. So the question is, many international organizations like IPCC in 2018, COP21 in I think it was 2016, and in fact, many nationally known and internationally known environmentalists are all saying much the same thing, that number one, we must not let the current fleet of nuclear power reactors stop burning clean or producing clean energy for us, because we need that energy in a essentially carbon-free form. The other thing is they're also concerned that we may need to build new nuclear reactors, perhaps as many as 500 worldwide, in order to meet the 3 degrees C by the end of this century that is the target for the current, I guess, the Paris Accords.
Yeah, so along with the environmental issue, a lot of the typical environmental groups are now getting on board with what we're what we're proposing here. One of them is Michael Schellenberger. He ran for governor in California in 2018. He was a radical environmentalist, anti-nuclear, just like Greenpeace, Sierra Club, but they are coming around. Even the founder of, I think, Greenpeace, was it? I think he's come around. Michael Schellenberger put out a really good piece talking against the Green New Deal because they didn't include this nuclear option in there. So can you talk a little bit about that? Who wants to do that?
So I think you've pointed out a few of the organizations that
Right.
have really changed their tune. I think one of the other ones that you didn't mention that's sort of remarkable is the Union of Concerned Scientists. They've traditionally been pretty anti-nuclear and anti-nuclear power as well as weapons, and have recently softened their position quite considerably. Additionally, there was an article in Time magazine within the last 2 weeks or so, an article by Hans Blix, the former Director General of the International Atomic Energy Agency, and there was another book that we've seen published recently, all making the same case that if you are concerned about the effect of carbon on climate, and if you believe that this is an urgent threat, which I think many people do, maybe most people do, there's no way to resolve that issue with expanded use of wind and solar. You really can't get from here to there without relying on nuclear energy. Nuclear energy, by the way, of all the energy sources that we have in the United States for electricity generation, is by far the largest non-carbon generating source of energy that we have. So for us to be prematurely shutting down existing nuclear plants and not replacing capacity with new reactors is really driving us in the wrong direction. And if you look at the situation in Germany, it's kind of a similar type of disaster. They, some time ago, because of the green movement, have specified increased reliance on solar and wind as renewables, and their anti-nuclear political forces have caused the shutdown of nuclear plants. And what has happened is, every time they shut down a nuclear plant, they replace that power with a new coal-fired plant. And so their carbon dioxide emissions are going up rather than down and contributing to the global issue.
I've actually got something to say about this. But I want to go at it from a slightly different perspective. Back in the day, which I understand is different for each of us, back in my day, the expression was first reduce, then produce. And I want to try to keep it in the context of a microgrid, because what we're learning in California under Title 24 and AB 32 is that for every dollar you spend on reducing energy consumption of structures, right, you're saving about $2.50 in the creation of new production capacity. And so thanks to a group like ASHRAE and international standards boards and what have you, on a local level, we are much more able to reduce the demand for energy in the first place. And as you do that, as you make your structures more efficient, and I'm not just talking about residential, but all classes of non-residential, you actually end up needing to produce less energy. So you've got a kind of a triple net savings here. And again, trying to do that on a macro scale, very difficult. But on a micro scale, communities, counties, regions can adopt this manner of going forward, where you're not needing to invest more in more production, which creates more opportunities for things to go sideways, just by emphasizing energy efficiency first.
Yeah. How many of you have taken advantage of UNLV's option to come out to your house and check your systems for energy efficiency? They do it for free, and you know they'll check your systems. They'll look at your AC system, your heating system. In my case, since I'd already swapped most of my incandescents for fluorescents and some of those for LED lights, they gave me 7 more brand new LED lights for free. They will do that for you. You know, I've got a 4,000 square foot, 2-story house. My worst electric bill during the summer is $200.
Wow.
And I keep it comfortable because I have a high efficiency air conditioning systems. You know, my normal bill right now is running less than $1 a day this spring. So yeah, do the right things to make your home energy efficient. It's really worth your time and effort and your dollars.
Just a second, just a couple of minutes here. Yeah, okay, yeah, we'll give you a chance in just a minute here. One of the things we've been doing for the last 2 years is, in addition to a Livermore type lab at the test site, we need to provide fuel for these new small modular reactors, and of course we can go dig it up, but are there other alternatives that we could find fuel for these reactors? Who would like to take that?
Well, the typical fuel for commercial reactors is uranium, which is mined. It's all over the world, easy to find. It needs to be enriched in one of the isotopes, uranium-235, in order for it to be effectively used in most reactors. As we go forward, there's been an increasing interest in higher levels of enrichment, up to about 20% enriched, which is considered sort of arbitrarily the threshold between low enriched uranium, which is not of real interest for weapons use, and high enriched uranium, which is getting into that range. So there is a problem in the country now to be able to supply the fuels for some of these newer small reactors, which have a preference for more highly enriched but still low enriched fuel, in part because that's one of the keys to giving you the ultra-long lifetime of 20 to 30 years. 20 to 30 years without refueling is kind of a pretty common target for these very, very small systems. So, but beyond that, with advanced reactors, some of the advanced reactors that are being developed under the Generation 4 program, there's great interest in a much broader application of different fuels, which are enabled by these new designs. That includes, basically reusing the energy content of already used fuel.
So some of the concepts use thorium for fuel as opposed to uranium. And my back of the envelope calculation says there's about 150 years worth of thorium in this country alone to power all of our energy needs if we had nothing but nuclear reactors in this country for 150 years.
Along the lines, one of the things that we were proposing to Congress is that we build a nuclear reprocessing facility out of the test site. Could that fuel be used for the future small modular reactors?
The product of reprocessing of spent nuclear fuel includes recovery of the enrichment of the uranium, which is already partially enriched. So, that part is sort of a no-brainer. But what I was alluding to in talking about some of the advanced reactor types, many of the constituents of spent nuclear fuel, which are the core of the problem of this very, very long lifetime of danger, are actually usable fuels in some of the advanced reactor types that we're talking about. And so I think in general, not talking specifically about the Nevada specific application, I think recycle of spent nuclear fuel and the use of advanced nuclear reactor technology would enable the energy supply to be multiplied by anything from a factor of 30 to 100 And so, even the 150-year time frame presumes that, we don't do repeated recycle of the spent nuclear fuel. If we do that, we get orders of magnitude, factor of 100 improvement in the resource utilization of the mined uranium. And I think that's the important consideration.
It's probably also worth talking about the question of if we were to reprocess fuel, and there was a program at one time called Global Nuclear Energy Partnership. The idea was we would design, build reactors and ship them places around the world so that we could provide power to places that currently were underpowered, thus relieving them from the need to build coal plants and use coal to move into the first world. But we would take the fuel back at the end of its spent time and reprocess it and turn it into more fuel that could go out. This was to address proliferation concerns about that fuel. We would own that fuel and we would take it back at the end of its life and we'd send them fresh fuel. I personally like that concept, and I wish it would come back. Now, the National Academy of Sciences did a study on the concept of reprocessing, and they determined that it was not cost effective, but that doesn't include questions about saving the planet from global warming. If you add some sort of a carbon cap or you cap and trade kind of a process, the calculus changes dramatically.
It also doesn't take into account the ultimate costs of disposition of unreprocessed spent nuclear fuel, which is like a big number. I don't think anyone can tell you what exactly that number is, but it is a big number.
Furthermore, there's reactor concepts out there that have a very fast neutron spectrum. That means that the neutrons are very energetic, and those neutrons can be used to treat used fuel so that the waste component of that is not as long-lived as for current kinds of used fuel. Down to, instead of tens of thousands of years, that would only need to be stored for maybe 100 to 300 years. So, I think that's a very interesting concept that we should be thinking about, as well as something like GNEP for solving the world's problems.
One additional weird fact about our environment, the first operating nuclear reactor that we now know of in the world was operating several 100,000 years ago in Africa. It was natural. There was enough uranium-235 and 238 in the soil that the reactor would start up. It would boil the waters out. It would stop. Waters would come back in. It would restart. They think maybe it operated for about 500,000 years, off and on, over weeks and months. The reason we know that is we go in and we look at the isotopes that are left there, and they're the proper isotopes that would have been there had you had that as a burning nuclear reactor in that time frame. So we know it worked. So nature did it before we did a long time ago.
Regarding economic development, can we become here in Clark County, Nye County, the leader of advanced nuclear technology by building a Livermore type lab and reprocessing and all of the other economic development opportunities that come with that?
Well, I would say that any major program in this area would bring great economic benefit to the region and to the state. I live in Reno, so I want it to be the whole state.
The whole state.
And UNLV will be a major participant, but so will UNR.
Yes, that's right.
And so I think that that's true. I think there's a word of caution that there already is a Department of Energy complex with national laboratories that view some of this area as part of their mission, their bread and butter. And so I think it's very important to think along the lines of what are the assets and characteristics that we have here in southern Nevada that are essential or especially beneficial to these kinds of developments. And at least for starters, to focus on those capabilities that are unique. They include things like the extreme remoteness of the test site from human habitation. It's probably unmatched anywhere else in the country. The arid climate, the expertise, the infrastructure, number of nuclear engineers, the fact that we've done it, and we've done it recently with one of these reactor test and evaluation projects. All of these things are very important, but they do somewhat narrow the mission. You can't do everything. But I think if this idea proves out, and if there are some projects that the suggestion that this be a national lab type entity wouldn't be far behind. But whatever the scope of this program is, I think it would undeniably bring economic advantage to the region.
Anything else? Well, that's pretty much it. I'm going to open it up for questions now. You guys keep the microphone, and I'm going to bring this mic around. So I'll start with you. Had your hand up first, so I'll come to you. Hang on. We got to get the mic to you, so it'll be on the video.
Hello, this is Cameron Hawkins, the founder and CEO of Arizona Energy. Currently, I'm the founder of the Clark County, Nevada Chamber, Nye County, Nevada Chamber, and I'm currently working on the Great Basin Chamber of Commerce. For me, when it comes to what you gentlemen are saying on the panel and the gentleman that's narrating today, fantastic. I've been, Mike, right?
Yes, sir.
I'm very, very much involved in looking at small development for gain, because that's how our civilization also grows. A lot of this has been very interesting to me ever since I was a pallbearer for Mr. Admiral Rickover. Okay, that was a long time ago. So I've been staying involved. And even when I was down in Antarctica, it was the same thing. They were still interested in it as well. What you guys are talking about is where we need to be. And I do agree that if nuclear on a small basis is definitely more palatable for mankind, which then would allow green to actually take place. And once again, that's my biggest challenge is what you said, Mike. Mike, the only reason why I'm talking is because of you. Not because of Berkeley. Berkeley's a nice place, but because of what you said. No matter who's in charge, they don't put their money where their money needs to go. The infrastructure goes to hell, and it falls apart. We've got over 40% of the state that cannot handle any grids changes at all. Got a nice little community in Boulder City that still has copper wire with paper over 40% of all the commercial buildings. And when that grid goes, it's over with. And when that solar plant offered them a brand new grid, they said no. So there's a lot of things going on. So my biggest question for your panel, and Mr. Florida here, okay, it's a nice place. I like Florida. Okay, I go hunting down there. My big question is, as you're rolling this out, I understand that you're going to look at it by tying it to the larger grid and then maybe separating. But if the larger grids can't even handle the infrastructure that currently is here because no one's, like you're saying, you know, you can lower your utility bills. I mean, look at how beautiful Nevada Energy has been working with what country, right? Been working with a foreign country to actually assist in the economic development in energy usage here, Norway. That has their contract for this state to reduce our energy. You see, so my concern is how, when you roll this out, which I would support this, and I'm a big green person, okay? Not that big. I'm only 6'4" in my boots. But the bottom line is, I support it because I love the small scale. I love how that can assist how we grow as human beings. But how are you going to address that everybody needs to be up to code before you put so much infrastructure and roll this out? Because the Colonel, I didn't get a chance to meet you when I was in DC, but I've studied you. You've done exceptionally well. I was a cargo handling training liaison for the Western Hemisphere when I was in the reserves. So there was a lot of diesels that we saw around the world. We'd go places and we'd have the state of the art. But we were state of the art in places where it was still a windmill running off of a piece of copper wire, even though there was Rolls Royces. So that was my biggest concern. I would love to support what you guys are doing, and I will support what you guys are doing, but I think we need to have also a little discussion about how we're going to prepare this to roll out. That's all I wanted to say. Cameron Hawkins.
Would any of you like to address that a little bit?
Part of what we're doing today, education, more people understand, more people hear about it.
Yeah, we're right now on the beginning of this. We have to start somewhere, and these are all great suggestions, and I'm sure we have, you know, with your help and other smart people, we will definitely address these issues.
So let
Go
me
ahead.
add one thing to that. How did this all begin in terms of commercial nuclear energy in the United States and the world? The military developed submarine propulsion reactors. The Eisenhower Atoms for Peace program declared that we needed to bring the benefits of nuclear energy to the far corners of the world, and the shipping port reactor, which was basically a naval reactor, was started up as the first commercial reactor, and that technology that proliferated. I'm not saying it did it without a plan, and I think that the planning needs to be there, but what we're talking about here that I think is interesting is a military installation application, which could be the leading edge for the kind of progress that you're talking about.
So one other thing we need to think about is make sure we understand the vulnerabilities to the current grid so that we can fix the right problems, and we're just beginning that process.
One of the things we were going to have on the agenda, but we were running just too long. I mean, we could do this all day and still not be done, whatever done means. But one of the clips, I would like everybody who is not familiar with Michael Schellenberger to make a note mentally, if not physically, to check him out, because he is one of the leading environmentalists in the country who is getting listened to. And if you do a Wikipedia search for pro-nuclear environmentalists, you will see hundreds of people that were willing to put their name on the internet as pro-nuclear environmentalists, and you'll see dozens of companies formed just for the purpose of producing pro-nuclear education and support. We had hoped some of them would actually participate today, but because of all the craziness that's going on in Washington, hardly anybody is yet ready to stick their neck out and say, I'm bipartisan, you know, I'm all in. And this is what we were hoping to come out of today's event, was to build an action plan that follows up some of the years, decades of research that's gone on, and apply that on an education basis. And Marty Wallman just got back from Washington, and if he'd like, he might want to comment to that, where he met all our congressional representatives, or most of them, and the staffs. And when you put on the side endless political arguments over Yucca Mountain and plutonium storage, and talk about the future of our country, the future of economics in Nevada, and the future of what cost-effective, safe, and reliable power would be for the rest of the country. Notice on the light up there, even look how much of the United States is blacked out. Well, it's obviously the Rocky Mountains and related areas, but with small nuclear reactors, you don't have to be blacked out. You could be on a mountaintop and still have power without a grid. Yeah. I knew we needed that. We needed that. I was born and raised in Oklahoma, so we'll have a conversation about that. Anyway.
David, okay, I'll go ahead.
So thank you, first of all, very interesting. I'm a new resident. I'm very interested in economic development, diversification. You've made the point that that's there. A key element in that value chain, as you've already mentioned, is kind of probably the fuel reprocessing. And what frustrates me as an engineer and a scientist is, my understanding is that technology is fairly well developed in France, Japan, even in Russia, and that there were activities in West Valley and South Carolina and stuff that started it that were all shut down by our previous, I think, fair to say, largely democratic administration as a result of phobias about this sort of stuff.
Yeah, I wish it was just a phobia issue, but apparently the official reason that Carter stopped it, he said this will stop proliferation. If we stop reprocessing, other countries will stop reprocessing. That will limit the amount of plutonium and uranium available. Didn't happen, but that was his official argument when he did it.
So I just want to, I don't want to keep the mic, a very short question. From how do we have to make that happen? I mean, is it an education issue, or do we need to vote in more Republicans, or you know, what's the recipe to maybe kind of get us from step 1 to 2?
It is an education issue in part. I don't know if it's necessarily a political issue with the sort of groundswell support from traditionally environmentalist groups. You know, that kind of leads you away from thinking that it's a purely partisan issue. It's maybe partially partisan. But I would say that in terms of the technology, you mentioned Russia, China, Japan, France, and you're right, that's reprocessing and recycle within the existing generation of reactors. The door opens for much more sophisticated technology if you have advanced reactors. And Argonne National Laboratory has been a leader in developing pyrochemical processing, which is a lot less, let's say, messy than aqueous processing, which is the standard. Now, the Russians are pushing forward with pyrochemical processing for advanced reactors. We've done research in this country, but we have yet to have a commitment to the idea of recycle.
That's one of the things we're working on with Congress. When we went 2 years ago to Congressman Amadei, that was one of the things that we proposed to him. He actually had us come to Washington to mark up the House bill to include that in there, and it's currently sitting in there. We just need to keep it moving along. So I can't comment.
Yeah, 2 questions as I'm thinking about this, and I'll just ask them both, and maybe I should, maybe I shouldn't, but you can address it. First question is, what is the implementation and the goal as far as, let's say in 25 years, what % of our power will come from something like this if you guys, you know, had your way and we started kind of getting the social will and all that? What could we be seeing in terms of, you know, what's feasible, and then what are the main bottlenecks towards getting to that point?
Well, we're currently running about 20% nuclear for electricity generation in this country.
But not with small nuclear reactors. With
No. So I think the plan going forward, you know, we'll be lucky to sustain that on the path we're on. Sustaining that, you know, will require, you know, new plants to replace the old plants, and it's easier to do that with a big plant than with 10 small ones or 1,000 micro ones. You know? So I mean, I would say that objective, which is probably more in tune with where the environmental groups are most focused. That is, we need large quantities of output of nuclear energy to offset fossil fuel supplies. So personally, you know, the French get about 80 to 90% of their electricity from nuclear energy. I think that's too high. They have countries nearby that they can export excess to, because overnight they don't need that much. But nuclear reactors, the large nuclear reactors, want to run full power all the time, don't change anything. Base load power. So for base load power, You know, I mean, I think in our country, 20% is the current level. I would like to see us sustain that. I think if we went up to 40%, that could have a major impact on some of these other issues that we're talking about. But that might be the level that you want to be. Nobody here is saying we should discontinue solar or wind or hydro or any of these others. But I think there is an observation that those so-called renewables are not adequate by themselves to solve the problems that we're facing.
Okay, so, but we're talking today about small nuclear reactors, and the video you started with were small nuclear reactors. So the 20% number you use, those are from places, you know, like the Gila River place and all that, that are large nuclear. Small nuclear reactors are still close to zero here?
We're talking about solving two different problems.
Okay.
You know, one is assured power for critical facilities. The other is powering the entire energy requirement of the country, and what mix are we going to use. Now, they're not unrelated, because the technologies that we're talking about at the micro level easily scale up. It's a lot harder to scale down. And so, for example, right now, it's very difficult to introduce a new advanced reactor technology at the large size. I don't know, you got $8 billion you want to invest?
I'll write you a check.
How about 100 million? 100 million starting to sound like, yeah, for a major new initiative with government support, that's achievable. And that reactor technology, in many cases, can be easily upscaled to larger output.
So one of the key issues related to your question is licensing. In this country, it takes a very long time to license a new technology, and one of the hopes with small modular reactors is that because of safety and perhaps even security and other kinds of concerns, if you can build them underground, that the licensing process could go much faster. But so far we haven't seen that with the one new project, the NuScale project. They've already spent $500 million trying to get their reactor licensed, and they're still probably a year away from that.
The other piece that I think would be a high benefit for the smaller ones is construction time. Go back into the late 60s, early 70s, I talked to a nuclear engineer who had walked in, and I think it may have been India, with the plans under his arm. 3 years later, they were producing electricity at the nuclear plant. We could be doing that and could have been doing that in the U.S. We aren't. I'm not going to figure out what I think the reasons are, but it can be done. And so the smaller the facility, the sooner that plant can be producing electricity and selling it. So that's another thing that the microgrid or the small module can help with.
How are the small grids vulnerable in terms of cyber? So you've got StuNet out there, you've got other things running around. How are they connected from an InfoSec point of view?
So much of the vulnerability of grids to cyber is what's called SCADA, and I forget what SCADA stands for. It's basically electronics that controls how the grid is connected to. Thank you. I did know that at one time. But interestingly, the nuclear power community has been very aware of this potential problem because they were some of the first to worry about cybersecurity. And they have addressed that by using things like air gaps so that their network does not talk off-site, at least for the critical portions of the facility. Others are beginning to learn that. It's very difficult to protect a larger grid from that because it's so diverse and interconnected. But we are beginning to learn that, and a whole new organization within, I'm not supposed to talk about, some organization that I shall not mention, has created a whole new department to focus strictly on cybersecurity for the grid.
They already did. Real quickly, I've got two quick questions, but it shows where we are in the planning process. What is the cost of one SMR? somebody's got to have it if you got to write a check.
You know, it's one of those things that you don't know the actual cost until you build it.
Yeah.
But some of these, let's go to the micro reactor level. Some of the figures that I've seen have been in the range of $100 million for something that's a 20, 25 megawatt output with no refueling for, say, 20 to 30 years. So it seems like a big price tag, but that's typical of nuclear power. Big price tag up front, but fuel costs averaged over very, very long periods of time.
But that's a question somebody's going to ask when we're trying to move it forward. The other question would be your SMR, it moves around. Is it a mobile dirty bomb? How do you deal with that argument?
So the Army is really sponsoring new work in this area, and they're very concerned about that whole issue. So there are a number of different things that you can do. If you have a compact system that can be buried, you've now provided additional protection against kinetic attack, for one thing. Another thing is that the fuel form is very important. And a couple of the reactor concepts that I know are responding to this requirement use something called triso fuel. The fuel itself is encapsulated in small spheres that are multiple layers, and that provide a layer of containment and protection under normal operations, but should they be dispersed, they still provide a certain level of containment protection. So there are a number of different things that you can do. Personally, if I'm looking at candidate system types for reactors that you're going to put potentially in harm's way, I would stay away from the ones that require pressurization in order to maintain safety, like water-cooled, or certain other ones, like a sodium-cooled reactor has a coolant which is very reactive if it's the coolant system is penetrated and there's a release. So the way I view it is that I probably would put those concepts off to the side and look at other ones that can be basically inert in the event of total disability. With a lead-cooled reactor, for example, if everything fails, the lead just freezes and encapsulates the whole thing. And walk away safe is a term which is perhaps a little bit of an exaggeration, but it's the idea that's important.
So when we're moving these things before they're operated, they're not very radioactive, so they're not very dangerous. Secondly, I don't remember the number, but the number is available online. Tens to hundreds of thousands of shipments of radioactive materials all over this country. It happens all the time. We've only had a few accidents, and there's been no significant release of radioactivity from any of those events. And that's available online. I just can't remember the exact number. The other thing is you don't want to do stupid things like advertising that you're moving a dangerous object, right? You don't want a big sign that says stay back 50 miles just in case, So you want to be discreet, and we are discreet, and that's why it hasn't been a problem.
I just want to thank Jim for his leadership in this, too. We appreciate it in bringing it to everybody's forefront here. I appreciate I'm very interested in the reprocessing part. So you had mentioned the study that was done. So was that done for fuel reprocessing for fuel for the current reactors that are old technology, or for the micro reactors or the small? And then second part of that question, 25 megawatts does how many houses approximately?
So the study that was done and the work that has been done at Argonne National Laboratory is originally focused on pyrochemical processing of advanced fuels. That's not oxides. It would be nitrides or metals or maybe carbides. I don't know. But the ultimate product that they put out had basically two feeds leading into a single pyrochemical processing advanced reprocessing facility. The one feed starts with existing fuels, oxide fuels, and converts that material into a form that could then be subjected to pyrochemical processing. and the other was, straight in to the pyrochemical processing. So
Okay,
that's been
so
well thought
that's all
through.
a little over. So is this reprocessed into the reactors we have now, which are older technology, or is it easier to reprocess it for the smaller? Because my understanding is those are a lot lower level.
Now, once you've done your reprocessing and you've basically partitioned the elements, you can do whatever you want with it. But the reality is that certain constituents of that reprocessing partitioning are not really suitable for use in existing generations of reactors. The Russians and the French and the Japanese recycle mixed oxide fuel, but they can only do it a couple of times. And then these constituents become degraded so that, there's a very strong limit. But if you go to the advanced reactors, things get a lot better.
Again, mixed oxide fuel. We primarily use uranium-238 at about 95%, uranium-235 at about 5%. That's our pretty much standard current light water reactor fuel. Once that reactor starts, when some of that uranium fissions, it turns into plutonium, which is also highly fissionable. So after 6, 8, 9 months, the fuel that's in there, it's producing about 25% of the reactions from the plutonium. So mixed oxide fuel, we separate out the remaining U-235, we separate out the plutonium, separate out the remaining 238, and put all three back into the new fuel. So we start the reactor off with some plutonium fissionable fuel in there instead of just the uranium as the primary fission. It can be done, but now that fuel, when we transport it, is a little more radioactive than the current standard fuel is.
How many houses does the small micro power?
Just real quickly, there's a gal with a question in the back, but if you assume that a typical house uses about 3 kilowatts of energy at any given time, just do the math, divide it. I think 3K is a good usable number, right? I don't know if somebody has a better number, but awesome.
We'll pass it to her in a second. A couple of quick comments, and I'll pass it on. I'm Darrell Lacey from Nye County. Some of y'all may know me for Yucca Mountain Days, but I won't talk about that. First half of my career, I was in the fossil fuel energy business, so I do know a little bit about the energy grids and those types of things. So, but to follow up on a couple of comments here, you were talking about feasibility of it and licensing times. One of the things we need to, I think, try to really encourage here is DOE and DOD are both self-regulated. They do not need an NRC license to build a small modular reactor. And if we can convince them to actually take the lead on this, we could get something done very quickly. And the Nevada Test Site's a great place to do it. And then just one thing for everybody here that you may not even realize about where we're sitting here is that we've shut down all of our coal plants. We've got about 20% of our renewable energy during the daytime. So we're at 80% natural gas during the day and about 100% natural gas at night. How many natural gas pipelines do we have here? One.
Hi, my name is Mike Venozzi. I work actually for Congresswoman Susie Lee. I believe that several of you visited with our office in Washington, D.C. a couple of weeks ago. I've been listening for about an hour on this thing. I've been listening, to a couple of different things. I do want to bring up a couple of things that I think are missing from the conversation. One, we are facing an 11% cut to the Department of Energy from Trump's budget that just came down the pipe. Now that budget obviously has to make it through the House of Representatives, the appropriators there. But I do want to say that, programs like ARPA-E being zeroed out, programs like the Department of Energy facing steep cuts, that does play into the adoption of new technologies. Now, regardless of how you feel about a particular technology, whether or not you support it or not, I'm not a scientist, but I do think that the money that has to pay for these technologies needs to be there in order for them to exist. So that's all I wanted to say. I do appreciate you inviting us to this event. Thank you very much, NDIA, for hosting us this afternoon, but just wanted to say that. Thanks. We don't know yet. We haven't seen anything to... One of the things that happens here... So one of the things that happens here, this is specifically, I think, what you're highlighting here is Creech and the Department of Defense want to do this on Department of Defense property. Let's see what they bring forward, quite honestly. Let's see what they bring forward. Let's see what the Department of Defense brings forward and what they do want to spend money on. If the department brings something that has to get the approval of Congress, we will look at it at that time.
I gotta go. If this group or another group were able to provide you with data on cost savings.
Yeah, I do want to let this lady. I do want to let this lady go first, but where I think that some facts need to be invested here is that the elimination of the advanced research and projects for energy administration. This is an advanced research project for energy right here. And the proposal of the elimination of that budget is something that I think we do need to inject into this conversation.
Could I just like toss out a, I can't really, oh, sorry. I'll try to talk into the microphone. Again, coming from the perspective of the microgrid, this is not a new technology, and I feel like we can move forward with the microgrid concept under the banner of small is beautiful, and these other pieces will find their way into the equation if we just keep working in that direction. Miramar in San Diego has now got a model microgrid system in the works. 29 Palms is being upgraded. These do not represent resource-heavy investments in concepts that will work regardless of any other consideration. I don't think it would be wise to let funding considerations at this moment in time stop the work that we need to do.
Okay, before you cut me off. I had concerns about many of you supported solar energy. My real concern is that solar energy and the panels are temporary. They give a 20-year warranty, and that's not enough to spend all that money, to me, to put them on. And then where's the dump pile for the panels? They can't be recycled. So we're creating a big problem there. I also have a friend who tried to sell her house, and her husband decided, oh, let's go solar and put panels on. Well, he died, and she could not sell her house. They put a lien on her house until those panels were paid off. So there's just other issues I have there. Thank you.
So I wanted to respond to the last comment, if I may. So I worked for a Democrat on the Hill and in the House of Representatives, and we had a very similar budget last year with the same cuts to ARPA-E and many similar cuts that we're seeing this year. And the Congress, in a bipartisan way, approved a budget that put the money back into ARPA-E and many of the other energy efficiency and renewable programs that had been cut by the president's budget. So I wouldn't worry too much about that.
I had a question on if someone could comment on TerraPower. I think that Bill Gates is behind that. And they have I think it's a sodium gas-cooled nuclear fast reactor, they call it. I think it's called the traveling wave reactor. And I think part of it's being funded by Los Alamos. And he's a very rich man, to talk to the gentleman about with Susie Lee back there. And what do you know about that? And can you comment on that?
Well, I have a few comments on it. That concept has been around for a long time. One of the earliest examples of it is something called the Teller Ishikawa wood reactor, which was developed by Edward Teller at Lawrence Livermore Lab. Lowell Wood was a protege of Edward Teller, and Lowell Wood was basically the founding force behind the TerraPower initiative. Now, the current concept, they have a traveling wave sodium-cooled system. They're also working on a molten salt type of system. And this is very advanced, very kind of out in front of the headlights type advanced reactor technology. I don't know where it goes, but Mr. Gates has friends in high places and a big bank account. So I think it's something worth watching.
His most recent concern is licensing. Licensing has been so difficult and timely in this country that he actually went to China to try to develop that same concept there. Unfortunately, he's also fighting something called ITAR, I think that's right, tech transfer to other countries. We're concerned that the Chinese will simply steal our ideas and then begin exporting them and cutting us out of the loop. And they've done that over and over in other technologies, so we're worried about the same thing happening here.
Hello, my name is Ron Solomon. Talking about solar and wind power, these two things are the biggest myths that are facing us. The problem with solar wind power, and you were asked this earlier, is a big thing. Reliability. It's not reliability. It can be generated at times that you don't want it and generated overly when you do, so a tremendous amount of this is wasted. There's no place for it to be stored, and also it's generated in places where you don't need it. So in essence, what happens is, even though the production of it, when it is produced, might be cheap, in many instances it's not, the problem is that because so much of it is wasted, the price when it finally gets to the end user is astronomically high. The countries in Europe that went heavily into this, Spain, Italy, Portugal, Germany, Switzerland, Holland, Sweden, their electric bills are 3 times as high as ours is, over 30 cents a kilowatt hour. Think about it, ours is on average 11. So every time, and unfortunately this state has bought into this nonsense in these last resolutions that were passed. So in other words, when you look at your electric bill, it's $150. If we go all the way down the road on this, it'll be $450 to $500. I want everybody in this room to understand that and tell you all your friends about it. Next time you hear this pie in the sky about this solar and wind, it's ridiculous. There's not enough wind and there's not enough sunlight to power the 5 cities in the eastern part of the United States that beats down on the entire Western Hemisphere.
How many of you saw the helicopter de-icing a wind turbine recently? Did y'all see that?
Thanks. I have a question on the licensing issue. I know that Yucca Mountain is being proposed for, to get back in front of the NRC for licensing. Does that process have to proceed in order for Nevada to be in a position to accept spent nuclear fuel for reprocessing, even if it doesn't involve Yucca Mountain?
Here, hang on.
Nye County, of course, has always been considered a supporter of Yucca Mountain and has also supported all these other nuclear activities that we're talking about. They mentioned GNEP up there. Nye County actually had volunteered to be a site for GNEP, and one of the public hearings was held in Pahrump a few years back, if you go back and look at that. So we have had a long history of working with DOE and these guys on that. the licensing process for Yucca Mountain is essentially the same licensing process you go to for any other nuclear facility, and it is potentially a very long and arduous situation, and there have been several small modular reactors sitting within the NRC for quite a few years, primarily because the cost and time to do it. Several of these companies have lost financing or other things. It's tough to keep a bank happy when you're sitting there looking at a 10 or 15-year licensing process to get approval. And my concern is that the NRC is very concerned about safety and does a good job on things, but I don't think they're capable of licensing new technologies. So that's why I think that if DOE or DOD would build one of these, show that the concept works, show that the concept is safe, then the NRC could take it from there and move towards newer construction licenses, but not necessarily having to develop the technology safely.
Yes, but the question of accepting the spent nuclear fuel for reprocessing, that was kind of the end part of my question.
The concept of GNAP, as they were mentioning, was to actually reprocess that fuel into a fuel form that could go into one of these other advanced reactors. And they mentioned TerraPower. One of the advantages of the TerraPower reactor that Bill Gates is working on is that it can utilize the waste streams that come out of this. Kind of the challenge you've got is that you can't just take a spent fuel rod out of an existing reactor and put it into another reactor. It has to essentially be chopped up, dissolved in the acid, separated, and then you can take some of those isotopes back into a new fuel form for whatever reactor you're looking at doing. So there's the challenge is I think there's somewhere between 16 and 20 different small modular reactor designs floating around out there right now. Each one of them has different pros and cons to it. Some of them are fast spectrum, utilizing different cooling methods. Some of them are just smaller light water reactors, different needs on what you're looking at. If you look at most of the commercial power generators, that when they talk small modular reactors, they're talking a 200 megawatt light water reactor that's just a smaller design, easier to construct, current technologies. Most of what we're talking about here are newer technologies that until one of them's built and runs, it's difficult to truly get through the licensing process.
So maybe this is a good time to, we have to wrap up soon, but to also fill you in on my trip last week regarding this. But first, just to emphasize that this is, with NDIA here, this is the first step is for Creech. This is the test case. And then, just put in perspective, we wanted to educate you about the technology that we're saying would work for Creech, and then Creech would have its own microgrid. Then prove it out at Creech, #1 place. Then it starts multiplying to other bases. Then the Army makes a transportable version. And then after maybe 10 or 20 years, after this is proven to be a really great thing, then the civilian sector would have assurance of its safety to then start moving it into our neighborhoods and casinos and whatever applications. We start building them. That's where the momentum is, and eventually the large grid starts getting replaced by all these little grids with their own power source, being these reactors. So, but here today, just to keep it in perspective, we're talking about Creech, but all the education that had to go behind that so you could understand why Creech and how this is the first step in that, whatever that saying is, a journey of 1,000 miles begins with the first step. And lots of people in here have been doing lots of things to then come to the point where they come here, and this is the first official public step. And then along with that, I really think, yeah, it's a total, like Stu, you mentioned about Republican. I got a tremendous Democrat reception in D.C. last week. You know, I went in and they were open and they wanted to hear about this. So I think we have to, it's total bipartisan kind of thing. And because again, it's like we said, the Pledge of Allegiance. We're all Americans here. This is for the military that protects us. Military gets confidence and uses this, it multiplies, ends up in the civilian sector eventually, benefits all of us 30, 50 years from now. The question, what happens if the grid goes down, doesn't exist anymore. That's the big picture of the end result. But us here today, we're working the Creech application, the test case here, to get this through. So along with that comes like the military budget. You know, they have a number of things like Tyndall Air Force Base got wiped out. They have a lot of expenditures in places that they weren't counting on. And if we want our $300 million or whatever to get this going, we need to figure that out, and that has to be a military thing, and we're going to need the support of sponsors in Congress for this. Now, there's probably a couple around the country, and you'd worked with some that, you know, we can get sponsors from around the country, one or two, whatever, here or there. But I think it'd be really cool if this is understood within Nevada, and for sponsorship. This is where it starts. Nevada is the starting point for this. If we can get Nevada political backing for this and working with this, that makes a very strong statement, because then it's a real Nevada thing. So again, I just want to put across, it's not Democrat, Republican, anything. It's just, I just want to let you know that my trip last week was hugely successful. I was on cloud 9 after that, and the reception I got in talking to people. Dean Titus's office, they didn't have anyone. They're kind of tight staff, but the person I briefed last week says, I'll do my best to come in by Zoom. I know I saw numbers coming on, one or two, I don't know if she got them, but she had class tonight. So even though the local office couldn't do it, she was willing, 3 hours later there to do it. So across the board, the support with our leadership now is very enthusiastic about this. From the briefing on it, they understand this isn't Yucca Mountain, this isn't the plutonium shipments, this is the new thing. They understood that. And as human beings and fellow Americans, they're interested in this. I got great support. I've had many emails back and forth this week of great support. So this is where we're going. So if we can get that swell of support for Congress from Nevada, wonderful. And Samantha back there, she's just been terrific from Congressman Horstman's office. Last week, they had an offsite back here in Las Vegas, so their door was closed and newspapers were piling up, so I didn't get to brief them there. However, right here, she's right here. So, yeah, we have to recognize that the interest as fellow Americans and human beings and the future of this country, there's great support and interest, and from that perspective, it's not partisan at all. It's for doing what's right for the country in the big picture. And it's probably not going to, it'll help some of us in our lifetimes here, but again, this is 30 to 50 years from now when the big grid disappears, because it's been like payphones. I was just at the airport, and it's like where all these payphones used to be, charging station. It's like, who would ever think that payphones would be replaced by charging stations? That's the kind of transition we're talking about here, and it's going to take some time. But this is the first steps for that. And again, I keep saying this, again, it's like this is an American thing for the future. Right now, the power could go out. The grid might not go down for 20 years or even 30 years. But on the day that it did, because the Earth was on the wrong side of the sun when that solar flare came off, or whatever, terrorist thing, or whatever, who knows. Or there's even been power outages where they really don't know what caused them. We don't know. It might never happen, but if it happened and the country was down for power for a week, 2 weeks, a month, America, as we know, it's finished. And if it happens with the world, we're back in the Stone Age. Your cell phone would work until the cell station, they couldn't get diesel fuel pumped and trucked to the cell station for the diesel generator that's there to keep it going. So just picture, never mind your food going bad, what if you couldn't use your cell phones for a few days? It's like we're talking catastrophic thing. And it all gets down to the idea that all our great stuff that we depend upon, the ability to supply power for them, has not been well thought out. It's been kludged together. And that's what we're addressing here. And the path forward from that is to get this darn thing going at Creech. We get sponsorship from that locally, make a strong statement for Nevada, get that going. It gets multiplied through the military. This greatly benefits Nevada's growth, eventually ends up in the civilian sector. Grids replaced eventually by all these microgrids and their own power generation, the big battery, the big nuclear battery, or the small nuclear battery. So I just wanted, because I saw, a number of things where it was maybe like, how does this connect to this? How does this connect to that? That is the big picture. And again, we're all together on this ship. And this isn't going to help us a day or a week from now, because this isn't going to be prototyped at Creech yet. But if we don't begin this journey, the journey will never happen. That's the whole thing. This is the first step of that journey. And in this room are the seeds for that, to begin making that journey. If nothing's done, 5, 10, 15, 20, 30 years go by, grid has an issue, that's it. It's like we hadn't done our homework the past 20, 30 years. This is the opportunity to be proactive. This is what it takes. People in this room, I view it as the beginning. It's the opportunity for the beginning if we take it. And we couldn't have better representation and people that understand things in here. So I really encourage, you've heard like a few of the people here. We got some time. We'll wrap up a bit, but networking, who should talk to who. I'm thinking like Cameron is your name. Like you said some great stuff. It's like whatever, I don't know if Samantha, we could talk, the 3 of us or the 5 of us or the 10 of us, but let's, as Americans and a plan for the future, let's just throw around some ideas and continue this conversation from today, because all the pieces are here. There isn't another group of people like this in the country. This is it. All right, that's what it's for. This is, yeah. So,
Thanks, Marty.
thanks. So, we'll put Jim back for the, I'm not good at the official stuff. I just talk off the top of my head.
Thanks, Marty. I'd like to thank everybody for coming, of course, and our great panel. How impressive are they, huh? Unbelievable. So we're pretty much done. Thank you for coming. Network, like Marty said, and let's get this done.
Just one quick comment. We're here today because of Bob Frank, Colonel Bob Frank, and I just wanted to thank you for making